Start.
Okay, so I'm started the recording on my end. So yeah, welcome to PFGM++, aka PFGM2 Electric Boogaloo. So the follow-up to the Poisson field generative modeling paper that we covered 2 weeks ago, I think. Uh, okay, so I I give a start by giving a brief recap of PFGM, and from there I'll show the derivation of PFGM++, which was just a couple of steps, uh, a couple of modifications on top of the base model and how we get there. And then I'll talk about some of the properties that come out and then the results. Note that I'm not covering all of the properties in the paper, but that's something I want to discuss later because I haven't understood exactly what the paper was meaning to say. So yeah. So as a recap, the original PFGM paper was based on physics. Essentially, the idea was you would take your original data distribution, say here as a plane, embed it and add an extra dimension so that you have n+1 dimensional space, and you would assume that your data distribution was an electric charge on this z=0 plane, and you would solve for the like you would compute the electric field associated with that distribution, and that would give you some vector field over the space. And if you followed the vector field, you had the nice effect that your data distribution on the plane gets mapped to a uniform distribution on this hemisphere as time goes on. So that was the base of their process, that your arbitrary distribution gets mapped to a uniform distribution on the hypersphere, and then in the actual paper they would project from the hypersphere on the hyperplane at the top here to simplify matters, but that was the basic idea. And so yeah, you would augment your dataset with some additional dimension z, and embed your dataset in the hyperplane z=0, and learn this normalized Poisson field e to the e of x, which is this term, which is 1 over the so Sn here is the volume of a hypersphere in dimension n, and you would integrate of x minus y over the norm of x minus y to the n+1. And the forward process would be simply following this field along the vectors, and it maps your data distribution to a known distribution on the hypersphere. So the original paper had a bit of a problem though, was that the training process was a bit complicated because you had to sample first a large batch of BL to approximate your field, and then you had to perturb your the like you had to sample a batch of data to approximate the field and a batch of data to actually learn the field, and then you had to perturb them in a bit of a complicated way. So even though your actual loss was fairly reasonable, the sampling process was complicated, and there were like other problems. Like first of all, you need a large batch to approximate the Poisson field. That's expensive. It's an overhead when you're trying to train your model. But also the minimizer is a bias estimator because yeah, I think you can see this gamma term, which is there to avoid dividing by zero, but it also means that your the minimum of your loss function is slightly biased, so it's not quite the true field that you'd like to learn. And also because you had this complicated thing with sampling a large batch of data points to approximate field, that made it not super compatible with paired sample training, which is what you need for conditional generation. So all of these problems were made PFGM, although the actual model were competitive with diffusion models, the training was a bit of a problem. And so one of the main contribution of the PFGM++ is to actually address that problem by completely getting rid of the old training process. So the first thing they do is that they generalize the model by not just adding one dimension, but adding d new dimensions. But then actually you throw all those dimensions away. You only need one extra dimension, but then d still sticks around in your equation, but just as a real valued hyperparameter. Although I think in the paper they only use integer values, but in principle you could use arbitrary values of d. So yeah, at this point d is just a real valued hyperparameter, and you don't need you're not needlessly increasing the dimension of your model. And then on top of that, they change the objective. They use a perturbation-based objective inspired by denoising score matching, and the rest, as we'll see, is maybe profit. So because this was a problem last time, I made just a slide for notation. So when I have x and y without any tilde, that's just the unaugmented data points. And I assume that my data distribution is just p of y. And the main assumption on this distribution is that it has a bounded and also compact domain, so it doesn't go to infinity. You also and so whenever there's a tilde on top of my variable, that means I've augmented them with here z for PFGM, but just my extra dimension for PFGM++. And again, this ascendant here is just a constant, which is the volume of an n-dimensional unit hypersphere. Just a constant. You can sort of ignore it as we go along. So yeah, so the first thing we do is adding these d new dimensions, and the like what happens to the electric field is very straightforward. You just have to add d to a constant here, and the denominator, the norm denominator here is just n plus d, and that's pretty much the only thing that changes. And the resulting field, you still have a vector field over your space, but define a surjection between your data distribution on the n plus d dimension hyperplane and the uniform distribution on the n plus d dimension hypersphere. And it's a bit of a problem because it's a rejection, you not get a map straight from your data distribution to the n plus d hypersphere, but luckily, and this is much easier with this figure here. So remember that when you have your distribution of hypersphere, you can always project on some hyperplane at some maximum distance, and that's equivalent. And if you look at it this way, basically the electric field, the field E that you're trying to learn, it's invariant under rotations under that field. So imagine that this is my projected hyperplane for PFGN, and okay, then we have simply a bijection, like a two-way map from the original data point here, or data distribution here to the distribution on this hyperplane, or here it's a straight line. In For example, for d equal 2, you get not a straight line, but just a cylinder around your data set, around your one dimension. But so that's like this red piece gets mapped to just a ring on the cylinder, but the the field is invariant under rotational, so any slice for a particular angle you'll have the similar curve under moving to another angle, and so you can sort of ignore all these rotations on the cylinder and only keep one. And so that's how you get like the end of the day, you only need to keep track of the distance from your cylinder to the data set to your unaugmented data distribution. So the only variable you keep around is this distance, because you can just ignore the angle part. So the actual augmentation you do is simply add this r distance, which is simply the norm of z, and you can do some calculation to find that, okay, dr over dt simply evolves as this equation where it's very straightforward. You just have r on the top, you still have this so x minus y norm to the power of n plus d on the bottom, and the only thing you need to add is this your original data distribution, and we call this the r component of the electric field. Similarly, I don't really define it, and the paper doesn't really either. Actually, you have the x component, so remember that x tilde is just x and r, and so you have this forward process ODE where, again, as in the PFGM paper, you replace this time parameter by the R parameter, which is here your distance from your augmented space to your embedded data set. So for R or Z equals 0. And so you replace the equation with respect to R, and so dx over dr, simply the ratio of these two components. This part here being a scalar, so it all works out. So yeah, that was straightforward. The next thing, big thing to add is to change the training objective. So like if you look at the old training objective, you first had to get some p-train, so you had to find out um, like for the, I'm not sure which, I think this was supposed to be a some y. I think yeah, you had a distribution p-train, and then you had to sample a batch from your data distribution, and then you had to perturb, like you generated some points in your augmented data set by perturbing your one of your samples with respect to some parameters, and you were trying to minimize this, which is the normalized Poisson field, and you had this gamma term to avoid dividing by 0, but that was making your estimator biased, but otherwise still the Euclidean norm between your network and the actual vector field you're trying to approximate. The new objective in comparison is much simpler. First, you sample some radius r from some distribution P of r. Then you sample some y from your data distribution. And then you perturb it with a perturbation kernel to obtain a new point. And so that's nice because you only need to sample one point from your data distribution, one radius r, and perturb it to and that's one point of your loss, and you do that multiple times to get the expectation that converges. So, and yeah, remember that one nice property of the Poisson field was that you could easily rescale it by some scalar function. And so here, when we scale by r to the over the square root of d, that does not change the actual trajectory followed by the ODE, just the time scale at which it does it. And yeah, the only thing missing here, or the main thing missing here, is the perturbation kernel, where you make it proportional to this thing. And like one of the main results of the paper is that when your perturbation kernel is proportional to this term, the minimizer of this does give you the actual field you're trying to approximate. And you can actually factor this out as just taking a uniform direction in the sphere. So all you need to do is sample some, like the radius, and otherwise the direction in which you perturb, that's uniform. And so the end, you sort of had, like all you need to do is get this term that should be proportional to this term. Okay, so I can move on to the main properties. So the first really nice property is that as you increase the d parameter, which is your dimension, and it goes to infinity, you actually recover diffusion models. And so this is translated to by this property from the paper, where if you take the limit as d goes to infinity and you make sure that r, your radius, your radius parameter, is equal to sigma square root of d, where sigma is your variance parameter from your diffusion model, then you get that your field on the right here and the score matching, or the score matching objective, the score matching field on the right here, they converge to 0. So I forgot to make the limit equal to 0 here, but that's the main idea. And not only the fields are equivalent, also the training process are equivalent. So because you're trying to minimize this loss here, which is very similar to what happens in some diffusion models, the minimizer, so taking d going to infinity and minimizing this objective is equivalent to minimizing the equivalent diffusion objective. So really, as you go to infinity, you get diffusion models, and if you take d equals 1, you get back the original PFGM model. But you can take any kind of d between the two, and that leads to another really nice property, is that because you have, when you take this r is equal to sigma square root of d, that allows you to automatically transfer some hyperparameters from diffusion models to a finite D, and especially remember that we still had this like distribution over the R's. Well, we can actually adapt any distribution from the diffusion literature and like apply this formula. So R equals sigma square root of D, and you get automatically the equivalent for the PFGM model. So that's a very nice property. A note on this figure here is that it's not super clear what they do here. So the idea is that you take some dimension and you take some parameter r, and you take the comparison as r goes to infinity, so you get further and further away from your data set, and you should expect this to be closer and closer to the uniform distribution on the hemisphere. And so they measure the total variation distance, which is a measure of distance between probability distributions. If you want to intuition, it's bounded by the KL divergence between the two. And so they measure, okay, just taking some R for various values of these and looking at the curve, what happens to the curve as you augment R, and you see, okay, it goes, it goes monotonically to zero, meaning you go to, you get closer to a uniform distribution. But if you use the R equals sigma square root of D trick, you see that they align. So this really means that you sort of get the equivalent kind of behavior for a diffusion model, but with some finite dimensional D in this case. And they give several examples of this hyperparameter transfer, where for one of them is EDM. They also show it for DDIM, but I'm not showing on the slides. And yeah, on the right here we have the algorithm for EDM, so the training and sampling, and the equivalent for PFGM using these hyperparameters that were directly transferred over. And the blue parts are um, the blue parts are the actual changes between the two. So that's a very nice result, because you get to automatically grab some of the existing results and do stuff with them. Speaking of results, so they do experiments on CFAR10 and FFHQ, and they report both the FID, and which you see that compared to the baselines, their PFGM++ does compete quite handily with the existing models. Um, Notice that an important fact that they notice that it's not the d equals 1 or d equals infinity that perform the best. It's some d between the two. So for CFAR10, it's d equals 2048, and for FFHQ, it's more 128. They also compare the number of function evaluations, which is a measure of how much computation you need. And here again, as they did in the original paper on PFGM, they showed that you could like reduce easily the number of function evaluations during your sampling process, and it still performed pretty well. So it's also technically cheaper. Note that the paper has a bit on exactly how they computed these FIDs, because they did some averaging like over multiple samples and had some interesting results there, but we can discuss that later. So to summarize the results, so for finite D values, you outperform the diffusion models, and the paper claims they reach SOTA in this case. And there seems to be a sweet spot between like the D equals 1 and D equals infinity. In this case, yeah, 2048 and 138. One thing that's I'm not discussing in my slides, but I really want to discuss, is that they mentioned that you can interpret the D parameter as controlling between robustness and rigidity, claiming that okay, the diffusion model sometimes has problem with the robustness, and I didn't quite understand the explanation, so we can probably talk about that. So yeah, I don't have a lot to add in my slides. So they fixed most problems with the PFGM, original PFGM model, especially the training process and the fact that they couldn't use uh, conditional generation, though they can. Uh, they actually get, because D is now a hyperparameter, you get a continuum between diffusion models and the original PFGM, and you get to steal all those really nice hyper optimized hyperparameters from diffusion models. You get to adapt them automatically to your PFGM model. So yeah, that's the end of my slide. Yeah, it was very fast. So any questions?
Yeah. I guess, does anyone else have questions before I start with my questions? Okay, if not, then yeah, I was mostly confused with this sort of R stuff, I guess. It's like that sort of thing where it was like, oh, the R is supposed to be the only thing that matters, I guess, or something like this. That's
The
that
small
kind of,
r parameter, or
yeah, the small R parameter, yeah.
yeah, I think it was the like if you remember the original paper, they were trying to find, yeah, the edits, they were trying to sample points in this hemisphere roughly,
Hmm.
and they had designed a whole like this perturb function. They had designed it so that you would get mostly a concentration of points near the original data distribution, and then as you would get further out, let's say, okay, this part of the vector field is not as important, so we need less points in that region. And yeah, really the idea is that you take of the new training objective, that you take one data point and you sort of like move it in one direction by some distance, and you control exactly how far it goes.
Yeah, but then as for this PFGM plus plus, they do something else with the you know dimensions and um
Let
yeah,
me
this
find
one.
it.
Oh
Yeah,
no, you
yeah,
sorry, before it was, I guess, the slide before this one.
this one.
Yeah, this one. Yeah, what I'm still kind of confused what's going on here. I guess it's saying, because it's saying only the R is needed, but I'm
Yeah.
not understanding why.
So um, so remember that the original paper felt a bit weird about this hemisphere business, because you assume, okay, maybe they have the whole sphere, surely. But like the reason they did this whole business, what they needed was a bijection between the distribution on your plane is equal 0 and some other surface. And so if you had the full sphere, you could not get a bijection, so you would not get a clean bijection between the two distributions. So that's why
Hmm.
they went for that pain.
Okay.
And here the problem is that all these parts here, they get mapped to this whole ring, so that you cannot get a proper distribution. But because like the field is symmetric, so if you take one, like imagine one of these curves and just rotate the field by some angle in around that cylinder, you get exactly the same curve. So
Okay.
that's what I mean by the like if you do, or the other way around, if you like take some point on the cylinder, rotate by some angle, you'll get the field rotated by that same angle. So actually, it's not invariant; it's equivariant. I should have wrote on the bottom. So because the as you rotate the field is symmetric, it doesn't, like, it's just you're just rotating the field around. You not lose any information by just keeping track of the R parameter.
Okay. Sorry, and this is supposed to be true at any dimension?
Yes.
Okay.
Like,
Okay. And then I guess, oh yeah, go ahead. Were you going to say something?
one way you can think about it is because you have this your field looks like this. where it's
Mm-hmm.
just okay some x minus y over the some norm. So the norm when you rotate it doesn't change. So you only have this term which
Okay.
is like it's immediate that when you rotate both vectors the or one of the vectors you get essentially the same field but rotated.
Okay. Okay. And then so go and then again to remind myself of you have the electric field. So is that like what we calculate? Is that what the like last time we talked about using Green's functions and stuff like that? Is that what that was again? I don't
Yeah, that's still the
remember
same thing.
exactly.
So honestly, I'm not even sure the Green's function stuff is really that much needed to explain what's going on. Like you could just say, okay, you're just trying to approximate this field that's inspired from electrostatic theory, and so it's just okay, this field that looks like this, and it has this nice property that your data distribution on the plane gets mapped to a nice uniform distribution on the hemisphere, and you can project it back to a hyperplane again to get something
Hmm.
that works well with your ODE solver.
Hmm.
And
Right. Okay. So this is for the forward process where we have the electric field, right?
yeah,
Okay.
but then for the reverse process, you just go the other way around on the field, and that's
Right.
yeah, just put a negative sign and it works.
Okay. Okay. And then yeah. So then okay. So how does the d hyperparameter affect things? So it's going to affect the norm, I guess. Like yeah, I'm just kind of wondering how does the d hyperparameter change things?
So I guess like if you imagine the what D does here, so assume that the norm here is the square norm. As you
Hmm.
augment this, so if the norm is smaller than 1, it sort of goes very fast to 0. If it's larger than 1,
Hmm.
it goes very fast to infinity. And so this sort of makes your norm a bit sharper. It's a bit like the if you've ever seen the diagrams about the like the p norms that are the variation of the Euclidean norm with different powers. It's similar to that idea, but the paper has some comments about how you should interpret the d parameters. So let me get back to those. I
Hello?
think it's bottom. Yeah,
Oh,
lower. Yeah, so they mentioned that D you can interpret as balancing the robustness and rigidity of your model.
okay.
So first of all, they have this figure here showing the first of all showing like here it's showing the conversions of your electric field to the score function. So you see that as D goes to infinity, it goes monotonically to zero, so you do get the same actual field. Then they also look at okay when you take this like training, so this R reduced from your sampling process. So when you like compute your perturbation of your data points, you compute the objective, and you look at the variance. You see that as D increases, the variance gets lower and lower. And so one of the effects of that means that as D goes as D gets higher, the variance gets smaller and smaller, and so it gets like these perturbations are stuck in one particular R. And so that's why what they're showing here. It's an effect in the also in the diffusion models where as your so I think X is supposed to be your no sorry sigma is your noise parameter so your noise parameter and X is your um, I think it's your data point and the there's a correlation between sigma and the norm of your perturbed sample for your training process, and you see that as D gets higher and higher, distribution here gets much narrower. And so they mentioned that this is sometimes a problem for diffusion models. I think they discuss in this parameter.
Mm.
So as noted, diffusion models are more susceptible to estimation errors compared to PFGM due to the strong correlation between sigma and the training sample norm, as demonstrated in the figure we just showed. And when D and R are very large, the marginal distribution PR of X is approximately supported on the sphere with this radius. So, and they say this can lead to problem, but this part I really haven't understood well what exactly they wanted to say. So yeah, the idea is that you have a high correlation between your when D is high, your when you perturb your data set, the actual radius of the perturbation gets really concentrated, and yeah, they mentioned some other papers that had similar problems, and they say, okay, taking a small d, um, so it broadens the distribution and maybe makes it a bit more robust. I'm still not sure exactly what they mean by robustness here, so that's
Mm, yeah.
my main problem. So yeah, thus we can view the d parameters as to optimize as to balance the robustness of generation against rigidity that helps learning. I still have no idea what they mean by these two terms, so it's mildly frustrating. But they do mention that taking some small d means you can do some more aggressive quantization, so get a smaller model, so presumably it's beneficial.
That's an interesting claim that they don't back up in any way.
I think they maybe back it up a bit more in the appendix, but I didn't have too much time
Okay.
to read it
Fair enough. Okay.
because I did not have time to look at these walls and walls of equations.
Yes. Oh gosh.
So yeah, let's sweep them under the rug maybe.
Yeah.
Let's see if they do
I think
say
that's
more
probably for the
about it.
best.
That's for sampling. So yeah, the phase alignment, they also prove that.
Yeah, I guess it's a little bit confusing what that is anyway, the phase alignment.
Yeah, I mean, I think they just mean that your model when training behaves as it would for the equivalent diffusion model.
Mm,
Yeah, so that's the EDM sampling. Same thing for DDPM, and I think that DDI, yeah, DDIM on the bottom. Yeah, they
mm,
they don't really seem to say much to back up those claims about robustness. So that's
yeah.
except for experiments, but yeah, there was this plot about they did some averages computation of the FID score over many samples, and when you look at this one, it's not super clear which one should be the winner. So you have like diffusion with the orange line, and
Hmm.
they overlap a bit, so it's not clear which one is the better. And
Yeah.
they on the bottom they have the moving average, which they claim shows that okay, the diffusion model does perform better overall. And on the bottom you have the 128. So I'm not sure which data set is this. Um, do they even
Oh,
say?
they talk about actually the quantization stuff up there. So I guess they did do something there with the
Do they?
robustness.
Where exactly?
Oh, it was up higher up, I think
Higher up?
you when you were scrolling. Right there, experiments for robustness,
Oh right,
and
yes.
then they have post trading quantization. So I don't know where those results are though.
Right. Okay. I
Maybe it's
think
some
they mentioned that
results.
if you're like okay, I think they mean robust with respect to if you take like a terrible ODE solver that has a lot of errors,
Yeah.
how well will the model respond to that? And they claim that the model is more robust when we take small d, which means that you can add some noise in
And then
your
also the other one is where they have less accurate weights, right? The quantization,
yeah
you lose the accuracy of the weights, and it's still able to work.
yeah.
So I think it's let's see. Okay,
Okay, I think they had
okay,
a
that's a little bit more concrete in terms of what
okay. I think they
robustness
had a
means.
figure for that, maybe lower. Nope. Where was it? I'm sure I saw it. I think maybe it was the main paper. Yeah, sorry, I haven't read all the details on the paper. I had
No
Actually
worries.
a fairly busy week,
It's
so
it's it's a
so
it's a
but it,
dense paper.
yeah, it's a dense paper, but maybe that last part of yeah, okay, this part. So model robustness versus D. So I think yeah, alpha is here the variance of the noise they add to the to the sampling process. They show okay for very
Hmm.
low D the noise barely affects the performance, whereas
Mm.
the diffusion you add noise and yeah it breaks down a bit.
Mm.
And I
Okay.
think yeah then they also do the same for the number of function evaluation. So as if you take larger step with your ODE solver, what happens?
Hmm.
I remember they had a similar plot in the PFGM paper. Oh yeah, okay, that makes a little more sense now. But yeah, when they explained it, it wasn't super clear.
Hmm. Okay.
Yeah, okay, so I don't know if we had any other questions about this.
Yeah, I mean, yeah, I was also pretty confused about the phase alignment stuff, to be honest. I don't understand what is the point of that, I guess.
No, no, over there. Um,
It's just like they set their R to some specific, it's just like a reparameterization of the R, I guess.
yeah, so I think it means like when doing this trick, it means that your finite D model behaves as the model with the infinite so infinite D, so as the diffusion model.
Hmm.
And I think the main reason behind, like the main utility is that if you use this formula, you can do the hyperparameter transfer thing where you, yeah, just take
Mm.
your diffusion hyperparameters that are well optimized and have been carefully worked to work better, to perform well, and just directly
Right.
apply them to your model.
And what about the total variational distance? What is that? That's measuring
Yeah, so
kind
the
of like it's like a distribution distance or something,
yeah, so
or what
the total
exactly is that?
variation distance is the so I think they describe it, but so to give you the intuition, the total variational distance between two probability distributions is the the maximum between any two events. So like if you think of a probability distribution as taking some kind of set of things that might happen and giving you the probability of that,
Hmm.
the total variation distance takes the maximum difference in the two probabilities that these your two distribution predict for a single event. Actually, so
Okay.
like I was looking it up on the on Wikipedia, so I can
Mm.
copy the link. So yes, the supremum between all the possible
The
events.
largest difference between the probabilities.
But yeah, I mentioned
Okay.
you can think of it as being bounded by the Kullback-Leibler divergence, or technically the square root,
Okay.
and
I
you have some
see.
other bounds. So yeah, it's just a
And so
distance
it's a
between.
distance with respect to a uniform distribution.
Yeah, in the paper they take the distance to the uniform distribution, which I assume is the uniform distribution on the hemisphere. So how close to so that like that's supposed to measure as you take this R parameter, which remember is how much you're perturbing your data point, and you want it as you go as R gets
I
much larger
see.
and larger, you want it to be actually close to uniform on your hemisphere. So
Right, right. Okay, I see. So I see. So basically, it's like the idea is that if you have different D, then you're kind of, I guess it's like trying to say your range kind of R will be different for each D, right?
yeah,
Because like here, yeah, okay. So like if it's with the low R, then you actually have to, yeah, it's with the low, wait, is that the low R? Yeah, with the low R, you can get to, you don't have to, sorry, with the low D, sorry,
yeah,
with the low D, you don't your range of R is much smaller compared to with the high D. So then, yeah, and then that's what you say, like, then this sort of free parameterization makes it so that now you use the sigma parameter and the sigma range remains the same for any D, and it will. your yeah, that range will be the same. And so then that's again, yeah, you could use that then for hyperparameter transfer because the range is exactly the same. So okay. Okay, that makes a lot more sense now. I was also, yeah, I was kind of confused by this particular figure as well. Okay.
Okay. Uh,
Um,
Anything else?
so yeah, can you go back to how this is equivalent then to diffusion? So in that equation, yeah, if so you plug in this R with this thing. Okay, so you have to just plug in R. Yeah,
Yeah, I
rho
didn't
equals
look
R.
much into
So,
the
okay,
proof, but I think they gave a sketch. Yeah, so by re-expressing,
okay, so it's equal to zero. They're saying. Okay, so they're saying as this goes to infinity, the difference between so and that was like the that left hand term is what we were learning in the PFGM plus plus, right?
yeah,
So
so that's your
okay, and then
PGF++ term, the actual vector field we're trying to learn, and the right is the score
that's the
matching
standard
field.
diffusion.
So that's saying
Okay,
the
and so
fields are the same.
okay, yeah, okay. Is the proof complicated?
I didn't really have time to look at it. Like they had give a proof sketch of saying, okay, you re-express
Okay,
the x component and the score in diffusion models, and the proof boils down to show that um, the limit of this term is approximately equal to the exponential term, which is your diffusion term.
okay.
So I mean,
That's what they're showing there.
they
Okay,
give a short proof, but I think the yeah formal proof to
okay,
appendix A3.
okay.
Actually, it's not maybe not the scariest one.
Mhm.
But yeah, I'm not sure. I'm not sure I wanted. Oh wait, actually, it does go a bit more into detail. So
Okay.
yeah, I do
Okay.
not want to
We
get
can
into
ignore
that.
it then. Yeah, okay. Fair enough. Okay. Okay. Yeah. How does theorem 4.1 and proposition 4.2 differ in any way?
So 4.1 says the
Uh,
fields you learn are equivalent. 4.2 says that the training
or the
process are
minimum.
equivalent.
Okay.
I mean, I've been triggered by this typo from the beginning, but I'll keep
Oh,
trying
that's
to
a good
ignore it.
point. Oh my gosh.
So yeah, they're saying that when you train with your PFGM++ objective, so this one, so theorem 4.2 says that training with minimizing this objective is equivalent to minimizing the diffusion, the score matching objective.
I
So
see.
that the
So,
minimizer, the actual model you get when you minimize are the same or equivalent, which is a different thing than these two fields being technically the same.
okay. Interesting. Okay. Okay.
Where the like the the diffusion, no, that's not the diffusion. Oh, actually yes, this is the diffusion
That's
objective.
the diffusion one. Yeah. Well, yeah. I mean, can't you just plug in? Okay, so if you plug in,
I think like they mentioned that the proof is basically showing that these two objectives are the same or essentially the same. So
okay. Okay.
I think they put it well here. 4.1 tells you the sampling processes are the same. 4.2 tells you the training processes are also the same.
I see. Does anyone else have questions? I doubt this is a paper that, people can understand on their first go. Like I'm kind of still like trying to figure this out, I guess. Trying to think if there's anything else that's confusing. This paper was very dense. Yeah. Uh,
Yeah, I'm glad we cleared up a bit the confusion as to what they mean by robustness. That was the main thing I was still
yeah.
confused about.
Okay.
Appreciate the presentation. Yeah, I tried to keep the awful proofs to a minimum. Well, didn't give any because I didn't think it would be very interesting.
Yeah. There's a lot of proofs here that yeah. I think it's yeah.
But
Well,
like
it's worth just
honestly, I
ignoring
think the
them.
proof you're probably better off ignoring the proof because they're
Yeah.
basically like it's almost like just paperwork. Like you formally prove that it's equivalent because you have to, but like you could also just be satisfied by the let's see the figure on yeah this figure here showing you that for example the the actual distance between the field
Mhm.
decreases and showing the
Yeah.
this one that tells you essentially the same. Well, no. Technically, this is the figure that tells you like experimentally that the fields converge to the diffusion one. And yeah, you could take that as enough evidence and not bother with the very detailed proof.
Oh, they have a Git repository where they
Yeah,
mentioned
yeah, they do have a
let's see.
repository where I mean they say pretty much the same thing. Um,
Right. But I guess they said that they didn't have much compute, so that's why.
I think they mentioned they had an 800 trade
Yeah,
to do their
they said they did
experiments.
not. I see that. Okay.
I think it's in the experimental details somewhere on the bottom.
Yeah, it would be interesting to see how this works on large data sets then.
I mean, yeah, maybe you need to send this to Astro and
Yes.
see if she can. Okay, no, yeah. So 4 NVIDIA 100s and 8 V100s.
Okay. Hmm. Okay. That's kind of and for CFAR 10 as well as FFHQ. Okay. CFAR 10 doesn't require. I guess if you want to run it in parallel, I don't know how long it took them, how many steps they did, all of that. You can run CFAR 10 diffusion models on a single A100. You just have to wait maybe like 2 days or something like this if you want to fully train it to the very best. But still, the FFHQ is probably more computationally intensive. Are they doing FFHQ at 64 by 64? What is their, or what's the
Uh, I,
resolution for FFHQ? Or was it the full
I think
resolution?
they mentioned they took FHQ as a higher resolution, but
Okay,
I'm
I see. But
I'm
yeah,
less
that will
familiar with
take
that
more.
part. I think it's
FFHQ is a good data set, I think. So it's not it's a little bit more of a complicated data set, I guess.
let's see. I'm sure I saw it. Okay, FHQ 64 by 64.
Oh, okay. They did 64 by 64. Okay, so it's not the full resolution.
Yeah, they also mentioned that for the backbone for the field, they use basically the same architectures that I mentioned in the original PFGM paper, being uh, DDPM and NCSN plus plus in both cases.
So the architecture from where? From NCSN plus plus.
Yeah.
Okay. Okay. Yeah. That's interesting. I guess they didn't use the OpenAI architecture, which was supposed to be the best. I don't know.
I mean, yeah, maybe we'll see Astro try and implement it and be very disappointed.
Yeah.
I don't know.
Yeah. Okay. So yeah, interesting. So this interesting that D is, I guess, kind of like supposed to represent dimension, but then I guess it doesn't really affect that. And so it's like having a high D does not affect like the computational cost or anything like that,
Yeah,
right?
yeah, that's the really nice thing is that you not actually need to add that many dimensions, which would, yeah, swamp your model pretty fast.
Okay.
But also, I don't think they do it, but you could take D to be just a real number, like 1/2, and see what happens.
Yeah. Okay. Okay. Are there any other questions? No other questions? I guess we all kind of need to read the paper again, I guess, or something. And yeah.
I
Or
had a
just
question, but I
try and
forgot
run
what
the
it was.
models.
Yeah. So someone have a question?
Yeah, I had a question, but I forgot what it
Yeah.
was.
I forgot what it
It
was.
was about the
Okay.
math.
It's
Yeah.
about the math. Yeah, there's nothing apart from math, so I guess that's what your
Well,
question would
there's
have to be
some like
about.
graphs and their architecture.
Yeah, yeah, but yeah. Okay. Well, I guess if you remember the question, you can put it in the chat.
Yeah, if you want to dig down in the math, maybe we can do that later this next week in the chat.
Yeah, for sure. Okay. Well, if there are no other questions, then yeah, we'll end for today. Next week, we'll talk about what paper do we have for next week. I forgot.
I think it was originally supposed to be Dashiell on reflected,
Oh, right, the reflected. Yes, yes, the
but
reflected
he told
diffusion
me
models.
that he,
Okay.
he probably didn't have the time after all. But I think he said
Oh,
he'd contact you about this.
I did not get contacted by him yet.
Oof. Uh,
Okay. Well,
yeah. Then
I'll
I may
confirm with
have
him
thrown you
again.
under the
Yeah.
bus.
Okay. I will confirm with him and see. But okay. If yeah, it's then maybe if he can't do it, then maybe I'll ask uh Molly or Murray in the chat to move up hers 1 week. Which paper was that? That was which paper did she want to do? She wanted to do the blurring diffusion models. So maybe you could do that instead. We'll see. Um, And yeah, if you guys have any other papers you're interested in covering, let us know. And then, of course, I have a whole list of papers that we can cover as well. Yeah. Um, okay, then I guess, yeah, I will see you all next week then.
Bye.